Well, I hope that you took a break, because I did. I went and smacked down on some Reese's Pieces, E.T.'s favorite snack and one of mine as well. Alright, so in the last video I told you that we are done with nomenclature. And we are, but we're about halfway through the lecture. Oh my goodness, what did he just say? Halfway done? Halfway finished? Yeah, I hate to break it to you, but this last half might go a little bit faster than the nomenclature did. And during the last half, we're going to focus on what we can do with alkanes. Well, we can't really do too much. I hate to break it to you, not at this point. So we're going to focus instead on physical properties and the way these groups are oriented, the way organic structures are based foundation-wise, and really relate to that on how it goes along with physical properties. Now, physical properties is a term that you should know by now. If you do not know about physical properties, then you need to go back to your general chemistry teacher and you need to ask for a tuition refund, because these are something that general chem classes should talk about and discuss in detail. But again, I'm not going to make any assumptions. I don't know what you took. I don't know who you took it with. I don't know where you took it. All right? So I'm not going to make any assumptions, and I'm going to teach this kind of on the basic fundamental level again. So physical properties are things that you can typically measure. These are things like density, melting point, boiling point, all of these compounds that do, or all of these physical things associated with the compound that will not change. Chemical properties compounds have as well, but that's more of how they react. All right. So if I'm going to do measurements on them, it's a pretty good physical property that I can talk about. There's going to be some physical properties that we're going to focus on with these organic types of molecules. The first one is going to be a boiling point. The second one is going to be a melting point. Very related. The third one is going to be solubility. And the fourth one is going to be shape and what we call orientation. All right, so these are all physical properties that we're going to focus on in the upcoming lecture videos for this particular module. All right, and this will help us finish out the chapter, and it will help us move on to the next greatest lecture theory in the class after that point. All right, so we can look for patterns. That's what this is all about. We can look for patterns. We can associate the shapes of the molecules to one of these four that I've written up on the screen, but there's actually more than this. These are only the first four that we're going to talk about, okay? And the first one that we're going to focus on is boiling point. I think if we're okay with boiling point, we'll be okay with melting point, but I'm going to strictly focus on boiling point first. All right, so boiling point, of course, is the temperature of which a liquid goes to a gas. The reason I'm starting with this is because most of the time, organic compounds, many of them, are going to be liquids. Okay, we do have solid organics, don't get me wrong. We do have solids, and that's why you're seeing melting point on the list. But unlike general chemistry, quite a few compounds that we have in organic are liquids. General chemistry, most of them were solids. You might not have associated that with general chemistry, but they were. They were mainly powders or crystals that, if they were changed over to solution, they were dissolved in a solvent, and then they were provided to you in a laboratory. So the majority of them started off with a solid at some point in time. You might have used them as liquid solutions, but that was not the what I would call the birth nature of those particular compounds. Organic, though, is a different story. Organic, we have many organics that are liquids. That's how they come to us. We don't need a solvent. They're already in a liquid form. And because of that, we need to talk about boiling point. So boiling point is the temperature at which that liquid, of course, boils and changes into a gas. Think of spaghetti water. All right, you've got this water on your stove, you're cranking the heat onto it, and that heat is making spaghetti water boil before you put your spaghetti in it, I hope. And over time, if you just let it boil, then all of it's going to evaporate off. And that's because it's turning into a gas after that point. All right. So we need to talk about chemistry. Okay, that's what this class is, organic chemistry. So we need to focus on the chemistry aspect of things. So for something to boil, what does this actually mean? All right, well, let's take water. All right, here's a little water molecule, and there's a water molecule. They're kind of cute, aren't they? And here's a water molecule, and there's one, and here's one. All right, so with these water molecules, they love to hang out with themselves. All right, they're very particular. So the water molecules begin to order themselves up. They're kind of OCD in a way as well. So they want to make sure that everything is in its place, everything has what it needs, and they want to make sure that everyone is lined up and happy. And this is the structure of water. So what that means is that this oxygen, it's negative, and it's going to be attracted to these partial positive hydrogens, all right? So that's what these things are going to do, and this is how they're going to begin to get structured. So in a way, we can almost say that these little red lines that I'm drawing in between these structures, that's the glue that's holding these molecules together. This glue is what we're going to call a intermolecular force. So there's intermolecular forces and there are intramolecular forces. Okay, both of these we're going to kind of pay attention to. We're going to bring both of these into the picture. But these forces have to be broken apart. Now there's a particular type of name for this type of bonding. Okay, those red lines, it is a type of bonding. And we'll talk about that. Just give me another video or two to make it there. But we'll eventually get to that point. And these forces has to be cleaved. All right? So for boiling to happen, this is the structure of the liquid. We give it some heat. It gets hotter and hotter and hotter and hotter. And as it gets hotter, ping, 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 all of those bonds begin to start breaking. Okay? That glue that was holding those molecules together has now been disrupted. And when enough of them get destroyed, all of a sudden, these water molecules now are freed up. Yay! And then they go into a gas phase. Okay, so this is the process of boiling. For something to boil, the forces between the molecules have to be broken and they have to be kept apart. That's the other half of the story that people forget about. Not only do you have to break them, but you got to keep them separated. Because if they come back together, it's going to form a liquid again. That's condensation. If that water vapor begins to try to escape, and that water vapor clings onto something that's kind of cold and lowers the temperature down, then the water molecules are just going to start forming back on themselves again because, again, I told you, they like to hang out with each other and they're very OCD. So we get a reforming of a liquid once more, and that's condensation. All right? So the boiling point that we will abbreviate as BP of a compound depends on what we call the strength of the attractive forces. Now, there's many different types of these forces. We'll talk about some of them, but there's many different types. But it's the strength of the attractive forces between or among the molecules. The molecules play a decision. They do play a role in this factor. You know, water is going to be different than other organic solvents. Even in the family of organic solvents, those particular types of molecules are all going to behave a different way. So they really do have a very important role to play when it concerns boiling points and their boiling point temperature. Okay? All right, so let's talk about some of these forces. Let's talk about and introduce some of these concepts that we're going to start seeing. We're going to refer to this in the boiling point, but we're also going to be using these same types of forces in other categories as well. All right, so let's talk about forces. We know that there's different forces that are out there. All right. The problem here, though, we are only going to be focused on alkanes, and alkanes are mainly hydrocarbons, which are carbons and hydrogens. Okay, so forces, think of this as glue, and we're going to relate to this in terms of boiling point. Okay, so alkanes have carbons and they have hydrogens. Why did I make that a point? Why did I write that down? Well, to remind you that that's what we've done, mainly carbons and hydrogens. And if we're only talking about alkanes, that's what they are. If they were alcohols, then we would have OH groups. If they were amines, we would have NH2 groups. If they were ethers, then we have an oxygen in between two carbons. If we had alkyl halides, then we would have fluorine or chlorine or bromine or iodine, right? But we're only sticking with alkanes right now. So alkanes are just carbon and hydrogen. All right, so carbon, 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 and then we'll stack on the hydrogens to make all these happy. And there we go. Two elements. Let's look at their electronegativities. Their electronegativities are like 2.5 and 2.1. If you pull out an electronegativity chart, that's what you're going to see between carbon and hydrogen. So this particular type of molecule is nonpolar. There's not really a charge distribution here. There's not one atom that has more electrons than the other. There's not one that's highly electronegative to pull electrons inward to give us these partial positives and partial negatives. You know, this is truly, really a nonpolar molecule. You know, you compare that to something like salt, which is really Na plus and Cl minus. These are fully charged. Okay? These fully charged compounds, they behave a little different when it comes to boiling point. Do you know what the boiling point of salt is? I mean, I can't even get melting point of salt in our lab, much less the boiling point. Water. Simple little water. This is not a nonpolar molecule. It's polar. So therefore, this polar molecule has a negative end and some positive ends. Well, that leads to some charge distribution. That charge distribution plays a role in the boiling point of water. And the boiling point of water, you know, hopefully is 100 degrees Celsius. Well, these are nonpolar. Alkanes, I'm not really going to find polarity here. I'm not going to find these full charges like I would on the Gen Chem side of the house. That means that alkanes, very common to see negatives for their boiling points. That also means that some of these are gases at room temperature. It means that some of these will be liquids, but they will have really low boiling points. But it also means that some of these compounds could have higher boiling points as well. But folks, this is a completely different side of chemistry. This is organic now. It's not general chemistry. So, negative boiling points are going to be pretty common. So, this is nonpolar. But some of these organic compounds, in the terms of alkanes, they're still nonpolar, but they do have an extremely high boiling point. We have to put some heat into them to get them to break up, to get them to boil, and to get them to turn into a gas. Some of those boiling points are higher than the boiling point of water, but yet these alkanes are still nonpolar. How is this the case then? The reason, those charges that we talked about over here, this is only part of the story. Remember, I told you intermolecular forces with an S. Those charges are only one of those. There's more to the story. Okay, and more to the story is happening in the terms of organic chemistry, because we know that these charges are not playing a major role in the boiling points of alkanes. They just don't. These are neutral molecules. They do not have a charge. They're not very polar. So charges are not playing a factor in the forces that are holding these molecules together. So what is? Well, this is where the S of forces come into play. We need to talk about some of these other opportunities. And the first one is what we're going to be calling an induced dipole. So we just said these molecules have no overall charge. Okay, they just don't. I drew out an alkane. It was propane at the time. Nothing charged in it, nothing positive, nothing negative, nothing. So there's no overall charge to that molecule. All right. Well, this is what induced dipole means, a topic that should have been presented in general chemistry. Let's have a molecule. I'm going to just draw out a big old long slug. Okay? Just a rod, a cigar maybe. Think of this as a cigar. And this cigar-shaped like molecule is pretty even. No charges, nothing out of whack, nothing out of balance. But the issue here is that we get so accustomed to thinking about lines or sticks and dots that we think that these things are very rigid, and they're not. Those lines are not there, okay? Those bonds that we draw to connect those carbons, they are not actually lines that are there in the molecule. One of the things, the common misconceptions that happen with people. So this structure is very fluid in that aspect, meaning sticks are not there. Those sticks are really electrons, and these electrons move. Well, there's a chance, statistical chance, that electrons that are involved in this molecule, that's a glue that holds all of this stuff together, these are in constant motion. Round and around they go. Whee! I told you they're like little kids in a football field, high on chocolate. And there's a chance, a slim one, but it happens, that this molecule, at some point in time, with these moving electrons that happen, could become lopsided. Electrons stack on one side of the molecule and not so much on the other. It didn't mean for it to happen. It just happened. And at any point in time, if the molecules by random create a partial charge due to the electrons swimming around the molecule, then we call this an induced dipole. And the reason is because on this end, this side, there's more electrons. So therefore, this side will be more negative. On this side, there's less electrons. So therefore, this side would be a little bit more positive. Well, here's the story. It's a domino effect. If only one of these molecules do this, just one, then folks, it will then play a factor in the neighbor. And that neighbor sees this and go, uh-oh, we got a charge here. This side is partial positive. And all of these electrons go, wee, wee, wee. I like to be on that side because that's the positive side. And they begin to migrate over to that side to get near that partial positive charge that was created due to random circumstance. And then the same thing happens here. And the domino effect continues. It will continue to affect each neighbor as that goes on. And we get these partial negative, partial positive, partial negative, partial positives all the way down the chain. That creates glue. That creates a way for these molecules to stick together. And we call this an induced dipole, or induced dipole and induced dipole bond, because we are talking about two molecules that are coming together by random just because it became lopsided as far as the electron organization went. All right. Well, induced dipole goes by a different name. If this does not sound familiar, then maybe London dispersion forces will sound familiar to you as well. If this is the way that they introduced it to general chemistry, then that is what they were talking about at that time. London dispersion and induced dipole mean the same thing. All right. Now, this is part of a bigger category, and this bigger category is going to be referred to as van der Waals forces. Okay, so this is a collective term. Van der Waals forces is a collective term that means many different types of forces. So sometimes we don't want to talk about just one type, and that could be because the molecules have more than one type. And instead of listing them all out in one kind of shopping list that you've created for the intermolecular forces, we can just say van der Waals. So instead of listing milk and cheese and sour cream and cottage cheese on a shopping list, we could just write dairy. And that's what van der Waals forces represent. It is a collective term that represents a group of forces, and induced dipole or London dispersion is really a part of the van der Waals forces that we like to discuss and talk about in a chemistry type of course. Now, these induced dipoles, or the London dispersion forces, these are very weak. They are actually one of the weakest that's out there for these molecules to choose. The issue, though, is that the more of them, as they increase the number, the stronger they get. So the strength goes up. So if we have a bunch of molecules that come together and arrange themselves in this fashion, then that's great, because the more that they do that, the stronger that those forces are going to become overall. However, if I look at the individual force between two of those molecules, whoop, they're very easy to break. And all that it would require would maybe be a little bit of heat. And maybe that heat is going to be enough just from the heat of my hands. That's right. I can take some of these organic compounds that are liquids, and I can pour them into a boiling flask, and I can cradle that boiling flask with my hands. And the heat from my hands could be enough heat to get this to boil right there in front of me as I'm holding it. It's kind of strange when that happens, but it can be done. So very, very weak forces if you look at them individually. All right. But in order for something to boil, you have to overcome those forces. And that overlap is going to be a driving factor in this whole mess. All right. So what do I mean by that? Well, I started off with a cigar-shaped molecule, right? So if there's another molecule that comes into the picture, there's a lot of chances for these molecules to overlap, isn't there? All the way through. All right, well, that overlap creates extra strength, which probably would mean I need more energy to go in and cleave these bonds from each other so I could separate those molecules and pull them apart. Well, what if that molecule was not just long cigar-shaped? What if it looked something like this? The issue here is that these types of shapes, they do come together and they stick together, but the problem is that they're very limited. The overlap is what we're looking at here. Longer, straighter, cigar-shaped like molecules have more chances of overlap than these weirdly shaped, non-linear molecules do. So here's your trend. This is what I want you to take away from this. The greater number of times they overlap, the higher the boiling point. So, if I had a molecule, and that molecule was pentane, that looked like this, and then if I had another molecule that was 2-methylbutane, that looked like this, and then I had another molecule that was 2,2-dimethylpropane, that looked like this. They are the same number of carbons, the same number of hydrogens, all the way through and through. Don't believe me? Draw them all out and count them all up. But I could rank these in terms of boiling point at this time. I don't need Wikipedia. I don't need Google. I don't need a reference book. I just look at the structures, people. That's all that I need to do. I can do this much quicker than getting on the internet and trying to type it in. Long cigar-shaped, all carbons in a row. This next one, these carbons have a branch period. I've got a carbon sticking up, right? And then these, well, they have two branches, one here and one there, even more so. Rank them in order of increasing boiling points. That means my lowest one first. My lowest one would be this one. It's more branched. My second one would be this one. It's branched, but not as bad. And then the highest boiling point that I have is this one. And that's because it's a straight across shape. It's all about the shape here. That's what it's about. That long cigar shape, that long straight chain area allows this molecule to overlap much better than some of the others. And when those molecules begin to overlap with each other, it increases the strength, which increases the boiling point. So the highest boiling point out of the three is this one, and the lowest boiling point out of the three is the 2,2-dimethylpropane here at the very bottom. All right, so there's your trend. The trend, boiling point increases. Boiling point increases as really the molecule increases. The formula weight of the molecule increases. The bigger the molecule, the larger the boiling point. However, boiling point also increases when you have less branching that's going to be involved. All right. Okay, so here's an image of van der Waals forces, and specifically really here induced dipole-dipole. Here we have a molecule that's a neighboring molecule, and these get slightly positive and slightly negative charges, and these dotted lines that you're seeing in between, those are areas or the glue, the temporary glue that's holding the molecules together. As far as boiling point goes, here's you a list of methane, pentane, decane, pentadecane, and icosane. So this is 1 carbon, 5 carbon, 10 carbon, 15, and 20 in total. And if you look at your boiling points here, your boiling points are going up, 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 right? So as our molecules get bigger with more stuff, then our boiling points will also get bigger due to more stuff. Here's the way branching affects the boiling point. So we have a straight chain pentane, and that boiling point's 36.1. Then we have a branching that happens. Look at what happens to the boiling point. It gets lowered at 27.9. And then we have another branching that could happen, and that boiling point goes to a 9.5. So the more branching that occurs, the lower and lower and lower that boiling point is going to be. All right. Here is another example of that. Here is octane, and then 4-methylheptane, and then 2,2,4-trimethylpentane. Again, same number of carbons and hydrogens in all of those cases. And if you look at your boiling point, they begin to decrease with the amount of branching that begins to happen. So octane is 127, 4-methylheptane is 118, and 2,2,4-trimethylpentane is going to be 99. So there you go. There is your intro to your first trend on boiling point. All right, so hopefully that wasn't too bad, right? So when you come back, we'll continue this discussion with boiling point. We'll go back and talk about melting point as well. You'll see very similar things that happen with them. And we'll go through and talk about some differences when we begin to change up things and not necessarily keep it as an alkane.